Hello! Welcome to Squid Essays. Inking your academic pen. My name is Julie and I will be your instructor as we read through secret key ciphers. The article source is embedded in the video description below. Feel free to read along. Please note that you can get a custom, plagiarism-free essay for as little as $10 a page at Squid Essays. The link is in the description. Secret key ciphers are classified into two types: block ciphers and stream ciphers. Block ciphers are the time-varying transformation of group of data bits, and stream ciphers are the time-varying transformation of individual or stream of data bits. It includes internal memory in stream ciphers, whereas in block ciphers, no internal memory is involved. Stream ciphers are an important class of encryption algorithms because of their low hardware complexity and power consumption. They encrypt binary digits of plain text message at a time, using an encryption transformation that varies with time. They are fast and more appropriate, and in some cases mandatory, example in some communications applications, when buffering is limited or when characters are individually processed during reception. Because of their low error propagation criteria, stream ciphers are advantageous in situations where transmission errors are highly probable. A binary additive stream cipher is just an XOR operation of plain text and key stream bits. It consists of key stream, plain text and ciphertext in the form of binary sequences. Each secret key K is given as an input to the key stream generator that generates a key stream sequence. Since the secret key K is shared between the transmitter and receiver, the receiver can decrypt by XORing the output of the key stream generator with the ciphertext, obtaining the message sequence. Key stream generation plays a major role in the security of the system. Hash functions are commonly used in communication devices, especially for integrity verification and authentication of data and control packets. Basically, a hash function is a function that maps a message of variable length to a fixed length hash value that serves as an authenticator. Hence, a stream cipher based on hash function is a very good option in reducing hardware complexity of the crypto system. So a hash-based stream cipher with low hardware complexity is important in the design of many crypto systems. Based on the usage of hash function, the security of PRNG varies. A cryptographically strong pseudo-random number generator, PRNG, is the heart of any stream cipher. A pseudo-random number generator is a deterministic polynomial time-based algorithm, which expands short seeds into longer bit sequences. Two methods of producing cryptographically strong PRNG are LFSR schemes and O-wave function-based schemes. Linear feedback shift registers are the most commonly used stream ciphers due to the low hardware complexity and less power consumption. The main drawback of LFSR-based stream ciphers is susceptibility to attack due to the linearity in the structure. Two major schemes to destroy the inherent linearity in LFSRs are taking output through nonlinear Boolean function and irregularly clocking LFSRs, clock control generator. Boolean function can be used to combine the outputs of several LFSRs or outputs of different memory elements of a single LFSR, giving rise to nonlinear combination generator and filter generator structures respectively. Step 1, Step 2 generators, alternating step generators, shrinking and self-shrinking generators belong to the category of the clock control generators, CCG, where the LFSR generating the key stream is clocked at different intervals. The only drawback of irregular clocking is key stream period gets shortened, but as per the security it gives best results. A class of bit-oriented key stream generator, K, is proposed in this paper and is related to class of the ASG, alternating step generator. ASG belongs to the family of CCG class. Here, the key streams generated by K generator GK are of long period, high complexity and nice statistical distribution properties. It uses three feedback shift register R1, R2 and R3 in the generation of key stream. The first register R1 changes state as a usual FSR, feedback shift register, whereas the other two registers R2 and R3 are clocked using a clocking mechanism. After the clocking, the output bit is produced at the output of GK. Key streams generated by a GK are obtained by XORing outputs of three Albanian next shift registers R1, R2 and R3. Correlation attack is one of the powerful attacks on stream ciphers based on FSRs and is considered as one of the most serious threat against the security of stream ciphers. If a cryptanalyst manages to detect a correlation between the known key stream segment and the output of one LFSR, when regularly clocked, this can be utilized in a divide-and-conquer attack on this LFSR. So, proper key stream generation improves the security. Design of stream ciphers. This chapter deals with the proposals of 3 stream ciphers and the hardware analysis, periodicity and attack time of both the stream ciphers. Stream CIPHER1. Stream Cipher 1 is a combination of LFSR-based Toeplitz hash generation circuit and LFSR-based key stream generator circuit. LFSR-based Toeplitz hash function, let a message M consists of length M bits and the output hash P of N bits. In order to generate a matrix of order nm, we need nm elements. By using Toeplitz matrix structure, it is possible to achieve the matrix of order mn by using m plus n1 bits. The Toeplitz matrix is characterized by the property that each column in the matrix is obtained by shifting down the previous column and adding a new element to the top of the column. Let the initial state of LFSR hash be SO, S1, S2, S3, S4 equals 00010 and the LFSR hash polynomial BH, x, equals x5 plus x2 plus 1. Since the degree of h, x, is 5, n equals 5 and the number of message bits bm equals 9. According to Toeplitz criteria, it needs only m plus n1 bits, here, 9 plus 5 minus 1 equals 13 bits, in order to generate a matrix. So using the above-mentioned feedback polynomial and initial state, the 13-bit output sequence of the LFSR is SO, S1, S12, equals 00010101111. The Toeplitz matrix is formed by writing the initial state of the LFSR starting from the bottom as the first column of the matrix. The consecutive columns are obtained by shifting down the previous column by 1 bit and adding the new bit obtained after each clock to the top of the column. LFSR OP sequence equals 00010101111. Toeplitz matrix 5x9 equals 010111111. 101011101, 010101110, 001010111, 000101011. Let the 9-bit message be 000010001. Then the hash value is obtained by reversing the bits obtained by multiplying the Toeplitz matrix with the column matrix of the message. Hash value produced is 10000. 010111111. 101011101, 010101110, 000010001, T, 001010111, 000101011, equals 10000, T. The schematic diagram of LFSR-based Toeplitz matrix is shown below. In the figure, the control register and shift register together forms the LFSR, whereas the control register defines the feedback polynomial of the LFSR. The LFSR changes its state with each message bit. If the message bit is 1, the corresponding state is accumulated into an accumulation register, and if it is 0, the state is not accumulated. Schematic diagram of LFSR-based Toeplitz matrix. Model of key stream generator. Consider a message of length m bits and output n bits. Let key be the initial random seed, h be the hash function and xi be the hash function output after ith iteration, and s1, s2, s3 be the sequence of strings generated by deterministic function f. The first stage output is x1 equals h, key s1, that is, concatenation of key and initial string. To get the next string in the sequence of key stream, hash a modified version of the previous output string is concatenated with the new random bits generated by the deterministic function f. The mathematical model of proposed stream cipher is represented as below. x1 equals h, key s1, x2 equals hkey x1, s2, x3 equals hkey x2, s3, xn equals hkey xn1, sn, key stream equals x1 x2 x3 xn. Construction of stream cipher 1. Stream cipher 1 is a combination of LFSR-based hopeless hash generation circuit and LFSR-based keystream generator circuit. The structure of LFSR-based hopeless hash is shown below. Algorithm steps: 1. Whenever the input is high, the states of LFSR are loaded into the register. 2. If the input is low, the states are discarded. 3. Once again, if the input is high, 5-bit register is ORed with current contents in flip-flops of LFSR and previous output of register is modified by present XOR output. 5-bit register is clocked only when message is high. Hardware implementation: A0 to A4 represents the state of the LFSRT and is initialized. The feedback polynomial of the LFSRT block used in the structure is taken as h, x, equals x5 plus x2 plus 1. Since the degree of the LFSRT polynomial of the hash block is 5, number of bits in the hash output is n equals 5. Therefore mn equals 4, that is, the degree of feedback polynomial of string generating LFSRs is taken as 4. The number of bits in the input of hash function block m equals 9. The main blocks in the realization of the LFSR-based hopeless hash function are LFSRT and accumulator. Thus 9 bits input are serially fed to the hash function block. The LFSRT advances at state with each of the input bits. If the input bit is 1, the corresponding state, A0 to A4, of the LFSR is stored in a 5-bit register. If the input bit is 0, then the corresponding state is discarded. The next time when the input bit is 1, the states of the 5-bit register is ORed with the current contents of the flip-flops of the LFSR and the previous output of the register is modified by the present XOR output and is stored as a new output, Y0 to Y4. The 5-bit register is clocked only when the message bit is high. The final content of the register after all the inputs are fed to the hash function block is the final hash value. The keystream bits of the proposed model are the serial output from the hash function block. Results: the platform used is MATLAB for calculating periodicity and attack time, and Xilinx ISE 10.1 FPGA for hardware design. The periodicity of the model can be defined as n, 2n1, 2, mn-1, where m is the length of input to the hash function in terms of number of bits and n is the degree of polynomial. The throughput is defined as the ratio of the number of output random bits to the number of input random bits and is given by n, 2n1, 2, mn-1/m, which can be much larger than that of a simple LFSR-based stream cipher given as 2m1/n for a proper selection of m and n. For example, with n equals 4, m equals 8, throughput for LFSR-based stream cipher is 31.89 while that for the proposed model is 112.5. Period for LFSR is 255 and for the proposed model is 900. Period of the key stream equals n, 2n1, 2, mn-1 and attack time equals O, 2k. Periodicity and attack time of stream cipher 1, hash OP length n, bits, hash IP length m, bits. Period of keystream attack time 47 422 0.095 10 25 0.17 9 23 25 0.817 11 13335 4.817 13 157 619 206.9 11 15 337 755 1653.3. Table 1 shows the periodicity and attack time results for various m, n values. From the above table it is observed that the periodicity increases at a high rate and for high values of m, and the attack time also increases rapidly. The simulation results of LFSR-based hopeless hash is shown below. Stream CIPHER2. Stream Cipher 2 is a combination of LFSR-based filter circuit and polynomial modulo division circuit. For synchronous stream cipher, CRC hash circuit is generated first and it is combined with well-known LFSR filter generator structure in order to increase the periodicity and security of this classic structure. In a filter generator, the Boolean function combines outputs of different memory elements of a single LFSR. Structural block diagram of stream cipher 2. An LFSR of length m produces a keystream of maximum period 2m1, when the feedback polynomial is primitive. All stream ciphers based on this structure are also limited to this periodicity. The The periodicity of generated key stream in conventional LFSR-based stream ciphers can be increased by increasing the key size m. The key should be generated by a random source, and it is difficult to build a pure random or pseudorandom source to generate a key of large size. Throughput for typical LFSR-based stream ciphers is 2m1/m. It can be increased to a higher value by using some reseeding mechanism. Reseeding mechanism is generating a new seed after every 2m1 clock cycles. In stream cipher model, the modular division circuit, CRC hash circuit, is used to reseed the nonlinear filter generator at the end of every fundamental period of 2m1 clock cycles. The reseed key is the hash output obtained by passing the stream generated by the LFSR in filter generator as input to the modular division circuit. The CRC circuit should be designed in such a way that the security of the stream cipher can be very high. Considering fundamental period of 2m1, and stream cipher contains 2n1 periods of filter generator, a total period of 2n1 clock cycles is obtained. At this period, the LFSR in filter generator is to be reloaded with initial key. Shift register-based division circuit, the hardware circuit used to perform division modulo polynomial over Galois field GF2, can be implemented efficiently using LFSR. In GF, addition is equivalent to exclusive OR operation and multiplication is equivalent to logical AND operation. In CRC operation, which is division modulo an irreducible polynomial over GF2, is used to generate the cryptographic hash code, CRC code. In a normal CRC calculation, the CRC code is calculated as CRC code equals m x mod g x. If g x is a polynomial of degree n over GF2, then n is the hash value size in bits. M is the message to be hashed and m x is the message polynomial with degree n1, where m is the message size, and mn. The operation of division modulo a polynomial over GF2 is implemented through a simple LFSR with tabs or connections determined by the division polynomial. The schematic realization of cryptographic CRC hash by taking the division polynomial as g x equals x5 plus x4 plus x2 plus 1 is represented as shows the CRC hash using polynomial g x equals x5 plus x4 plus x2 plus 1. Experimental results: the periodicity of proposed structure in comparison with the pairs of polynomials to that of simple LFSR key stream generator for the same number of input random bits, same key size, is given in the table. Table 2 pairs of Q, X, key stream generation polynomial, G, X, division polynomials for maximum periodicity. Table 2 shows the periodicity and attack time calculation for various G, X, and Q, X, polynomials. Results of simulation of 4-bit LFSR with Q, X, equals x4 plus x plus 1 and G, X, equals x4 plus x3 plus 1 are shown in Table 2. The entries below each initial key in Table 2 shows the reseed keys generated by mod G, X, circuit at the end of every 15 cycles. The fundamental LFSR with feedback polynomial Q, X, equals x4 plus x plus 1 and initial key, A3, A2, A1, A0, equals 1001, gives output polynomial, A, X, equals x14 plus x11 plus x7 plus x6 plus x5 plus x4 plus x2 plus 1. This polynomial when divided by G, X, equals x4 plus x3 plus 1, in mod G, X, circuit returns the residuar, X, equals x plus x2 plus x3, given as 0111, in the first row below column corresponding to key, 1001. The residue, 0111, is loaded into LFSR as key for next iteration giving output polynomial, A, X, equals x13 plus x12 plus x11 plus x10 plus x8 plus x6 plus x5 plus x2. Table 3 residues given as keys at different stages for 4-bit LFSR. Key equals 1001, K equals 1000, 01, 11, 10, 11, 001, 1, 11, 01, 01, 1, 001, 11, 11, 10, 10, 1000, 001, 10, 11, 1100, 11, 01, 11, 10, 001, 001, 00, 10, 10, 01, 01, 001, 1000, 1, 1100, 01, 1, 1, 11, 10, 001, 101, 001, 1, 001, 01, 11, 11, 1001. 1000. Table 3 shows residues given as keys at different stages for 4-bit LFSR. Hardware implementation. The LFSR polynomial is taken as q, x equals x9 plus x4 plus 1, and the division polynomials are taken as g1, x equals x6 plus x5 plus x4 plus x3 plus 1, and g2, x equals x2 plus x plus 1. By using these polynomials we can generate a CRC hash. Once a CRC hash is generated, the output is sent through a nonlinear filter in order to get the stream cipher output. The expected results are shown below. The structure of proposed model is simulated using Verilog on FPGA Xilinx XC2S400-5PQ208. The hardware structure of proposed stream cipher 2 is simulated in Verilog. The periodicity and security analysis for various key sizes are done using MATLAB. The increased periodicity and security of the proposed structure is clearly visible from experimental results. For the key size, periodicity and attack time are compared for filter generator. Clock-controlled stream cipher. Clock-controlled stream cipher uses irregular clocking as a nonlinear function. The irregular clocking is more effective than other nonlinear functions. The main idea behind CCG is to introduce nonlinearity into LFSR-based key stream generators by having the output of one LFSR control the clocking of a second LFSR. Since the second LFSR is clocked irregularly, attacks can be reduced. CCG is classified into two types, the alternating step generator and the shrinking generator. This stream cipher design uses the alternating step generator. The alternating step generator uses an LFSR R1 to control the stepping of two LFSRs, R2 and R3. The key stream produced is XOR the output sequences of R2 and R3. The following steps are repeated until a key stream of desired length is produced. 1. Register R1 is clocked. 2. If the output of R1 is 1, then R2 is clocked. R3 is not clocked but its previous output bit is repeated. For the first clock cycle, the previous output bit of R3 is taken to be 0. 3. If the output of R1 is 0, then R3 is clocked. R2 is not clocked but its previous output bit is repeated. For the first clock cycle, the previous output bit of R2 is taken to be 0. The output bits of R2 and R3 are XORed. The resulting bit is part of the key stream. Description of a K generation of modified clock-controlled alternating step generator. K, a generator GK of the class. K is a binary key stream generator intended for hardware implementation. Every generator GK is composed of 3 feedback shift registers R1, R2, R3 of lengths L, M, N respectively. Let H equals 0, 1 and K equals L, M, N del1T, del2T. Be arbitrary vectors, where L, M, N are positive integers and DELJT, for J1, 2 is a decimation function that acts on R1, 0, 1 LA1, 2, 3, 2L. For any non-negative integer I, let R1I, R2I and R3I denote the elements of HL, HM, HN respectively, and Xi denotes the elements of V equals, HL, HM, HN. GK equals, K, FO, F1, F2, where FO, HLAH, F1, MOH and F2, NOH are the feedback functions of R1, R2, R3 respectively. If all the feedback functions Fj, J0, 1, 2 are linear, then GK is said to be linear. If FO is nonlinear but F1 and F2 are linear, then GK is said to be mixed. The first register R1, called the controlling register of GK, changes its state as a normal feedback shift register, whereas the other 2 registers R2 and R3, called the generating registers of GK, are clocked using a clocking mechanism. It works as follows: R1 controls the clocking of both R2 and R3. At one time t, only one of the last 2 is to be clocked, denotes the if bit of the register R1 by R1I, T. If R10, T, equals 1, the clocking of R2 is performed and the bits R10, T, R11, T, R1W1-1, T, are the inputs of a clocking unit, otherwise the clocking of R3 is to be performed and the bits R1J0, T, R1J1, T, R1JW2-1, T, are the inputs of a clocking unit. The clocking unit computes the integer value of these bits and returns that value plus 1. That is, at time t, if R10, t, equals 1, R2 is clocked L1t times and R3 is not clocked, otherwise R3 is clocked L2t times and R2 is not clocked, where Del1t equals R10, t, 1 plus 20 R1I0, t, plus 21 R1I1, t, plus 2 W1-1 R1E1, t, Del1t equals 0, t, 1 plus 20 R1J0, t, plus 21 R1J1, t, plus 2 W2-1 R1JW2, t, 40, W1, W2, L, and I0, I1, I2, E1-1, J0, J1, JW2-11, 2, L1, where t denotes the complement of Fry, t. After these clocking, R1 is clocked once. Once the clocking is performed, an output bit of GK is ready. The output bit is XOR of the outputs of R1, R2 and R3 of GK, K1 or the XOR of the outputs of R2 and R3 of GK, K2. Keystream Z equals ZT08 equals Z0, Z1, Z8 denote the keystream generated by GK, and Z is given by Z equals R1T R2P1, T, R3P2, T, if GK, K1, R2P1, T, R3P2, T, if GK, K2, R2P1, T, equals R2P1, T, 08. From the previous definitions it follows that all state sequences and keystream generated by GK of K1 UK2 are most periodic. GK is said to be maximum if and only if all its state sequences are periodic with maximal period equal to px, where px equals 2L, 2M1, 2N1, if GK is mixed or px equals 2L1, 2M1, 2N1, if GK is linear. The subclasses of mixed and linear K generators will be denoted by M, K and L, K respectively. Generation of delta function and state diagram, keystream Z of a K generator GK. K2 is a bitwise XOR of the irregular decimation of its generating sequence. R2T and R3T are governed by the decimation function Delt1 and Delt2. Thus it is difficult to expect a strong correlation, especially if polynomials of high Hamming weight are associated with the feedback function of the registers. The secret key K of GK consists of the initial state of GK and the decimation functions. The size of the key depends on the desired level of security. To achieve high-level security level, the choice of parameters are a control register size L128, generating register sizes M, N greater than 80, polynomials of high Hamming weights associated with the feedback functions of these registers and decimation functions consisting of small values for W1 and W2 ranging from 1 to 5. Such GK is resistant against well-known attacks. Egg. For a GK whose FSRs have length L equals 128, M equals 127 and N equals 125, any combination of the following values for W1 and W2 such that W1, W2, 1, 2, 3, 4, 5 satisfies the necessary conditions, L, max, U, M, max. Hardware implementation, Delta function generation and state diagram of clock-controlled circuitry. The hardware implementation is provided in the figures for LFSR-based GK with L equals 64. It can easily be extended to handle a size of L equals 128. For fixed width Delt1 and Delt2, where the widths are both 2, that is, W1 equals W2 equals 2, the overall output stream of GK is computed by XORing the outputs of registers R1, R2 and R3 of GK. K1, or only of registers R2 and R3 of GK. K2. Above fig gives the delta, for I equals 1, 2, function generation circuitry and clock-controlled circuitry state diagram and implementation. Here, each one of the two decoders sets exactly one of its 64 outputs based on the 6-bit index value, which is the input of the decoder. The LFSR3 content, that is, LFSR1, is ANDed with the decoder output. The single-bit output of each entry contains the selected bit of the first LFSR. At any time t, to compute the values of del t, the leftmost bit is multiplied by 2, which is effected through a shift-left operation. A subsequent addition of each of the weighted bits yields to the function del t generation. The number of decoders, entries are equal to the window sizes. The shift-left operator should also be adjusted in order to multiply each bit with its proper weight. The state diagram consists of 3 states, each corresponding to the clocking of one particular LFSR. The sequence of events is as follows. For hardware simplicity, first LFSR3 is clocked once. Based on the value of R10, t, the function del t is generated, which denotes how many times LFSR2 or LFSR3 are to be clocked. Subsequent to the clocking of the proper LFSR as many times as dedicated by the delta function. Again, LFSR3 is clocked only once. In implementation, one hot coding scheme is utilized. The 3 states are encoded as 100, 010 and 001. In this state, the down counter is loaded with the proper delta function, depending on the value of the LSB of LFSR3, which also determines the next state. Based on the values of this bit, the circuit transitions to either S2 or S3, wherein it remains as many clock cycles as the function del t. During these clock cycles, the counter is decremented. When the counter content becomes 0 Albanian like S, which denotes that delta cycles are over, the circuit transitions back to S1, wherein the counter is loaded with a new value of delta. In each state, only the corresponding LFSR is clocked, which is ensured by the 3 clock getting-in gates next to each other. In the process, clock buffers may be inserted in the proper locations within the clock network. The RTL schematic of clock control generator is shown below. Hardware implementation of proper clock control of 3 LFSRs, CCG block, is shown below. The entire block CCG is used in the above schematic for the control of LFSRs. Table 4 shows the comparison of various stream ciphers with parameters like periodicity, attack time, throughput and security are shown below. Parameter/stream cipher periodicity attack time throughput security stream cipher 1 high N, 2N1, 2MN1, medium O, 2K, high N, 2N1, 2MN1/M medium stream cipher 2 medium, 2N1, 2M1, high O, 2M plus CN, C less than 1 medium, 2N1, 2M1/M medium alternating step generator medium 2L, 2N1, 2M1, high medium 2L, 2N1, 2M1/M high. Table 4 comparison of various stream ciphers with different parameters. Conclusion: the design of 2 stream ciphers and the modified clock-controlled alternating step generator are made using Xilinx FPGA. Periodicity, attack time and throughput are calculated using MATLAB. This paper includes a class of key stream generators, K intended for hardware implementation. A complete description of the design of generator is given. The clock control introduced in this paper makes cryptanalytic attacks more difficult. As per the characteristics and properties, it is clear that the K generator is well suited in stream cipher applications. As per the results, the periodicity of stream cipher 1 is more compared to stream cipher 2 and the attack time of stream cipher 2 is more compared to that of stream cipher 1. It is shown that key streams of the K generator GK have large period, large linear complexity, high throughput and provides good security compared to the first 2 stream ciphers. Comparison of stream ciphers has been given in terms of periodicity, attack time, throughput and security. A proper design exercise on higher length of LFSR can give rise to very attractive stream ciphers for use in handheld communication devices and in other communication applications, which demand low hardware complexity and real-time operation. Please be aware that the free essay that you were just reading was not written by us. This essay, and all of the others available to view on the website, were provided to us by students in exchange for services that we offer. This relationship helps our students to get an even better deal while also contributing to the biggest free essay resource in the UK. Thank you for taking your time to listen to me. I hope you enjoyed learning about secret key ciphers as much as I did. Kindly remember that you can get a custom, plagiarism-free essay at Squid Essays for as little as $10. The link is in the description. See you next time.